So thanks a lot for the invitation. It's a great honor to be here to celebrate Russ's birthday. So happy birthday. So today I'm going to talk about random walk and dynamical percolation, which is joint work with Yuval Perez and Jeff Steif, who are both here. So before I describe the model and I state our results, I'm just going to fix notation and give a little bit of background. So what I'm going to be interested in is to estimate mixing times for random walks on dynamical percolation clusters. So first let me write the definition of mixing time that I will be using. So this is the total variation mixing time. So if we have X, an irreducible Markov chain on a finite state space with transient matrix P and invariant distribution pi, then the mixing time is the first time that the total variation distance from stationarity drops below epsilon. And I'm going to consider the worst starting state X, so I take a max overall X. So this is the total variation mixing time that I will be using. A canonical choice for epsilon is epsilon equal to a quarter, simply because after a quarter, the total variation distance decays exponentially fast, so we can just multiply it by log epsilon, log 1 over epsilon, to get any precision we like. Okay, since I'll be talking about percolation, if we consider bond percolation on ZD, so with probability P, an edge is open and 1 minus P closed, I'm going to write theta of P for the probability that the cluster of 0 contains an infinite number of vertices. So theta of P is going to be its standard notation. And from now on, I'm going to focus on the discrete torus, Zn to the D. So let's perform bond percolation on the torus. With probability P, we keep an edge, and with 1 minus P, we don't. And we do that independently for different edges. Then we know that if P is greater than PC, PC is the critical probability of ZD, then there exists a giant component that I will write Gn, or just G if you want, which has size of order n to the D with high probability. And all the other components are going to have size some logarithm in n with high probability, some power of logarithm of n if you want. So now, once we fix the giant component, we can perform a simple random walk on it. And we can talk about the mixing time of simple random walk on the giant component. So let X be a simple random walk on G. Then with high probability over the environment, over the random graph G, the mixing time of the walk is up to constants n squared. I'm going to give, so I will give references now. First of all, when I say with high probability, as I said, I mean the randomness is only on the environment G. So this theorem was first proved by Itai, and Elhanan Mossel for 2 dimensions. Then Pierre Mathieu and Remy proved it for all d greater than or equal to 3. And Gabor Bete gave an alternative proof, which also works in all dimensions. And I'm going to come back to Gabor's result in a little bit. Okay, so everything so far is static. So now it makes sense to introduce dynamics. So first, let me define the model of dynamical percolation, which was introduced by Hagstrom, Perez, and Steif in '97. So dynamical percolation. So we start with a graph let's say here we are working on ZD. So we assign IID Poisson 1 clocks to the edges of the graph. And when the clock of an edge rings, then the edge updates its status to open with probability p or closed with 1 minus p, and this happens independently for different edges and independently of the previous states of the same edge. So when clock of an edge rings, edge updates with probability p and closed with 1 minus p, and all of that happens independently of everything else. So this is the model of dynamical percolation, and in the paper where this was introduced, one easy statement was that if p is not equal to the critical probability, then with probability 1 there exist no exceptional times. So what I mean is that if p is above pc, then for all times there exists an infinite component with probability 1, and below pc, for all times there is no infinite component with probability 1. Now, if p is equal to pc, this is a groundbreaking result due to Garbon, Pete, and Schramm, who showed that there do exist times at which the cluster is infinite. And this built on earlier work of Schramm and Steif, who worked on the triangular lattice. Okay, so now...
Once the net is open, it stays open?
No, it has a Poisson process of... so if when the clock, it keeps...
And then it switches?
That's right.
Oh, well,
Yes.
Re-randomizes.
Yeah, it randomizes. It doesn't switch.
Re-randomizes. It doesn't switch with probability p. Okay.
Right. So I'm going to show a simulation a bit later of the full... No, I will show it anyway. I'll show a simulation of the model I'm considering. So now I'm going to define the model of random walk on dynamical percolation. So this was introduced a few years ago by Perez, Stauffer, and Steif. So again, we're going to work on the torus Zn to the d. And we're going to assign IID Poisson mu clocks to the edges. So mu is going to be a parameter of my system. So mu is going to be a parameter that depends on n is the side length of the torus. And the interesting regime is when mu is much smaller than 1. I'll come back to that in a little bit. So the interesting regime is when mu goes to 0 as n goes to infinity. I'll come back to that, why this is the interesting regime to look at. So we assign IID Poisson clocks to the edges of the torus. And again, so we perform dynamical percolation with parameter mu, and with probability p, the edge becomes open, and 1 minus p close when the clock of the edge rings. And now I'm going to place a random walk. So the random walk is going to be a continuous time random walk. It will have an exponential 1 clock. So when it is at a vertex, it stays there for an exponential amount of time of parameter 1. So x is going to be continuous time walk. It stays at a vertex exponential 1 amount of time. And when the clock of the walk rings, the walk chooses one of the 2D neighbors of the torus and jumps there only if the edge is present. Otherwise, it stays in place. When clock of x rings, x chooses one of 2D neighbors of the torus. And jumps if edge is present. Let me put only jumps.
Chooses, you mean uniform?
Uniformly at random, yes. It chooses one neighbor and it jumps there only if the edge is present at this time. So the reason here we are putting the exponential clocks on the edges of the graph instead of the vertices is because in this way the uniform distribution is always invariant for the walk. So let me write the state of the system. Xt comma eta t is the state of the system at time t. So this is a point in the torus together with a configuration of the edges. So an edge is closed if it is 0 and 1 if it is open. So x comma eta is clearly a Markov process. And as I already said before, by the way the walk moves, the invariant distribution of the process x comma eta is going to be the product of the uniform distribution on the torus and product of independent Bernoulli with parameter p. And actually, x comma eta is reversible with respect to this measure. But let me just focus on the invariant distribution for the x component. So this is the uniform distribution for all x. And I emphasize this because the exponential clocks are placed on the edges. So even though x comma eta is Markovian, if we only look at x, this is clearly not a Markov process. So in the paper of Perla Sousi and Steif, where this model was introduced, they focused on the subcritical regime. And they looked at the mixing time of the random walk component in this changing percolation cluster. So what they showed is that the mixing time is up to constants n squared over mu, where mu is the parameter of the edges. So let me, before I talk more about this theorem, let me just say briefly why we take here mu to be much smaller than 1. So the Poisson clocks, the exponential clock has mean 1 over mu. So by taking mu smaller than 1, 1 over mu becomes much bigger than 1. So this is saying that the environment is changing much faster than the walk moves. And the reason they consider this much slower. The reason they consider this regime is because, first of all, if one is interested in applications, of course here we're talking about the torus, but if one is interested in applications, then it's more natural for the dynamics to evolve more slowly than the movement of the walk. And secondly, from a mathematical point of view, this is the interesting regime to look at, because if mu was very large, then the walk would just behave as a scaled-up version of the simple random walk, so most things would just carry over. And actually, in their paper, one other thing they showed is that if you consider the same process on the whole of ZD, then for any value of p and mu, the walk x is transient recurrent, or recurrent depending on whether ZD is transient or recurrent. Okay, so then let's focus now on the subcritical regime. So what they were able to show is that up to constants, so whenever I write the symbol, I mean that there are universal constants, which do not depend on the parameter of the system, so that the mixing time is upper bound by one constant times this quantity and lower bounded by the other constant times the same quantity. So what this theorem is saying is that on the time scale of 1 over mu, the time scale at which the edges update, the random walk mixes in time n squared, which is the same as the mixing time of simple random walk on the torus. So on the time scale of the edges, the walk behaves like a simple random walk on the torus. And let me just say a few words about the proof. So the upper bound on the mixing time was proven using coupling, and the lower bound was proven using Markov type. So Asaf Naor spoke briefly today about Markov type. Markov type, I don't want to go into details about this part because I don't have so much time, but I would like to say a few words about the upper bound. And most importantly, their coupling technique relied heavily on the fact that the percolation was subcritical. And the reason for that is the following. I'll just give a very high-level idea because to carry out the details is quite complicated. So the idea is that the walk, so we are in the subcritical regime, so all of the components have small size. And while the walk is constrained in a small component, this allows enough time for the edges outside of this component. It allows enough time for the walk to lose information about the edges outside of this component. So when finally the walk moves this small component, if we try to couple two walks on the same percolation cluster, when these two walks leave the small components, it basically boils down to trying to couple two simple random walks on the torus. And that's why this takes time n squared. So on the time scale of 1 over mu, it boils down to coupling two walks on the torus. So as I said, this is just a very high-level idea of the proof. But I don't want to say any more about that because, as I said before, this relies crucially on the fact that P is less than PC because the components have small size. And what we want to look at now is the supercritical regime. So for P greater than PC, the coupling. So the process x comma eta is a reversible Markov chain, and then you can just consider a function of just the walk component, just the location of the walk. You are in the torus, so you just have to map it to r to the 2d, but it works fine. And exactly the same argument. So using Markov type, what they are able to show is that if you look at a small multiple of this time, then you haven't traveled very far, so you cannot have mixed. And actually, in the supercritical regime, using, again, Markov type, they were able to obtain a lower bound of order n squared plus 1 over mu. Remember, mu is the rate of the edges. So let me explain why this is a lower bound. So 1 over mu, you definitely have to wait for the edges to refresh. Not to refresh, but at least for the percolation to become supercritical. And then it takes n squared to mix, at least n squared. So then the open question was, what happens, how about an upper bound? Is the lower bound sharp, or what is the correct answer for the mixing time in the supercritical case? And this is what we focused on. So before I state our results, I would like to define what I mean by quenched mixing time. So we were able to show in certain regimes in the supercritical case that not only in the annealed sense we are mixed, but actually with high probability over the environment, what is an upper bound on the mixing time. So what do I mean by quenched? Suppose, let me just write it. Suppose that I fix the environment process eta for all times. So eta t is the configuration of the edges, and suppose that I give you a configuration of edges for every time t. This now gives rise to a time inhomogeneous Markov chain, the random walk on. And we can talk about the mixing time of this time inhomogeneous Markov chain. So I will denote the mixing time of this Markov chain as T mix of eta when the environment is fixed to be eta for all times T. So what we're able to show, is that, so we are always in the supercritical regime, but now I'm going to also add the assumption that theta of p is strictly bigger than a half. So theta of p is a probability that the 0 is connected to infinity for the full lattice, and in the case of the torus is the proportion of edges of vertices that are in the giant. So if theta of p is bigger than a half, then we showed that with high probability over the environment, the quenched mixing time is upper bounded by the lower bound n squared plus 1 over mu times some polylog factor. And this holds with high probability as n goes to infinity.
Perla, could you please explain again what is Tmax of the environment throughout time?
Yes, so if you fix eta, eta tells you which edges are there at time t. I mean, eta t gives you which edges are present. So x is now a random walk on the torus, which is the dynamics of x are governed by the environment eta t.
So it's not necessarily even connected.
It's not. Right. This is an environment. And so, but because of the way the walk moves, I have put the exponential clocks on the edges. The uniform distribution is always invariant. I'm not saying it's unique, but it's always invariant. And so I can talk about, so I just write as a subscript when I condition the environment to be eta, so I can look at this probability minus 1 over n to the d, the total variation of that. So mixing time of eta, I just mean that these become small. Okay, so our first result is when p is large. And second, in the case when theta of p is smaller than a half, so when theta of p is strictly positive, then we obtain the same result, but instead of looking at a fixed time, we have to take a stopping time. So same result for a stopping time. So what I mean, instead of taking time t here, I have a random time. Okay, so now in the remaining part of the talk, I'm going to explain how we prove theorem 1, and then I'll just give just a quick outline of theorem 2. So are there any questions on the statements? Yes?
Do you think there's actually a difference in behavior between...
No, I don't.
That's just the proof?
It's just the proof doesn't work.
You mean a specific stopping time or any?
Yeah, so I didn't explain it carefully, but so if you look, so for time homogeneous Markov.
When your mixing time is...
No. I mean, sorry, no, I said the same result, so I control the expectation of the stopping time. So we construct a stopping time which is with high probability upper bounded by the same quantity and also an expectation. So that's what I mean. So in the theory of Lovász and Winkler for stopping rules, this is another notion of mixing that they use, but for reversible Markov chains, this is equivalent to the standard notion. But here it's time inhomogeneous, so we don't know about equivalencies. Okay, so now I'm going to use to give proof ideas. So in order to prove it, we use the method of evolving sets, which was introduced by Ben Morris and Yuval in 2004. So I'm going to give a quick background on evolving sets. Morris and Perez from 2004. And I should say that this method is closely related to what Diaconis and Phil call strong stationary duality. So Morris and Perez, why were they interested in evolving sets? So their goal was to bound L infinity mixing times using isoperimetry. So let me define the evolving set process. So we have a Markov chain X, which is irreducible. So we have a transition matrix P and an invariant distribution pi. And we start the evolving set process from some state X. And then inductively, in the next set is going to contain all the Y's So the UI is an IID sequence of uniform random variables in 0, 1. So let me explain what I wrote here. So let's take, for simplicity, since this is the case for us, pi to be uniform. So I can cancel them. So what this is saying is that I include a point in the set Sn plus 1 with probability which is proportional to the number of neighbors that the point has in the previous set. So in the simple case where we perform a simple random walk in the box, if the evolving set looks like this at some time, then at the next time step, the evolving set is going to either gain or lose points along the boundary. So this is going to be the next step. So this is the evolving set process, which is a Markovian sequence of subsets of the state space. And from the definition, you see immediately that it can get absorbed either at the full space or at the empty set. Because we don't want it to get absorbed to the empty set, I'm going to condition it to get absorbed to the full set before shrinking to nothing. So condition on absorption to the full state space. Now, this is going to give me another Markov process, which is called the Dupe transform. And I'm going to denote it by S tilde of t. So S tilde is the evolving set conditioned to contain the full set before shrinking to the empty set. Okay, so I haven't explained yet why evolving sets are useful to bound mixing times. So this is due to a beautiful result of Diaconis and Phil. So let me state it. So Diaconis and Phil have constructed a coupling. So there exists a coupling of the walk and the Dupe transform so that they start from the same point. And for every time t, the probability that xt is equal to something, given the whole history of the Dupe transform, is given by pi of, is the stationary measure restricted to the set st tilde. So given the whole past of the Dupe transform, xt is uniform on the Dupe transform. So why is this useful to bound mixing times? So idea for bounding mixing times. So if we had a time t, at which time the measure of st tilde was large, so if there exists t, such that pi of st tilde is bigger than a half, say, plus delta, then at this time we would know that the random walk is uniform on a set with measures strictly bigger than a half. So this would mean that the total variation distance between the walk and the invariant distribution would be strictly less than half minus delta. So that would imply minus pi would be less than a half minus delta. And as long as the total variation drops below a half, then we can get to any accuracy we want by just multiplying log epsilon times. So this is how one bounds mixing times using evolving sets. So now let me go back to our setup. So here we have fixed the environment eta, and we have obtained a time inhomogeneous Markov chain. So this means that at every time we have a different transition matrix. So one can, in a straightforward way, one can adapt the evolving set process to the time inhomogeneous setup simply by replacing the transition matrix here by the transition matrix that the walk uses at the n step, n+1 step. So again, this is a Markovian sequence of sets, and it can get absorbed on the full. So if we condition it to get absorbed to the full set, then we're going to get again the dupe transform, and then the proof of dichotomous field goes through in exactly the same way to give a coupling in the case of time inhomogeneous Markov chains. So now, back to our setup, we know that at time t, the random walk is uniform on the evolving set. In this case, pi is just the cardinality. So as I said, in order to bound mixing times, we need to find a time t at which time the evolving set, the dupe transform, has large size. So by the definition of the evolving set, it's very easy to check that if you take the measure of Sn, pi of Sn, this is a martingale. And this is exactly the same in the time inhomogeneous setting. And also because we condition the evolving set to get absorbed to the full space, the dupe transform is a submartingale. Pi of St tilde is a submartingale. So pi of St tilde is a submartingale. So we know that St tilde increases in size as time goes on, but we would like to know by how much it increases. And in order to understand that, what we need to understand is the boundary of the dupe transform in this changing percolation cluster. So to control. So this means that we need to control the boundary of St tilde in the changing percolation cluster. And this is where we are going to use now Gabor's result. So let me state his theorem. So what Gabor showed is that if P is greater than PC, then the isoperimetric profile of the giant component coincides with the lattice profile. So more formally, what he showed is that for all subsets of the giant that are connected, and the size is not too small, so he just takes some power of logarithm and say upper bounded by the giant over 2, then for any such set, the boundary of the set in the giant is at least a constant times the size of the set to the power 1 minus 1 over d, and this happens with probability 1 minus little of 1 as n goes to infinity. So what this is saying is that if the set S has some substantial size, then the boundary is at least the size of the set to the power 1 minus 1 over d, which is the same as the profile in the lattice. So now we would like to apply this result to our dupe transform, St tilde. because we need to control the boundary of ST tilde in these changing clusters. So first of all, this result requires the set to be a subset of the giant. And of course, here there is no reason for the dupe transform to be a subset of the giant. But one can suggest, why don't we use ST tilde intersected with GT? So at every time, I just look at the subset of GT, which are the points that are contained in the dupe transform.
Okay. So I'm confused.
Yeah.
Right? You're working in continuous time, right?
Yes. So let's say that we discretize time now. I'm going to discretize time. And then if the discrete time mixes, then also the continuous one mixes.
So you fix A to T, and then you discretize time.
That's right. And then I look at eta t in the whole interval, but I only look at the walk at integer times. So now let's take ST tilde intersected with a giant. So if we knew that this was up to constants the size of the dupe transform, then we would be in good shape because we could apply this result to the intersection and get a good drift for all these times. And so then we would know how fast the dupe transform would grow.
So what is the relation between the expected increment of the ST tilde and the boundary?
Okay, so I don't want to write it because so one can find, because this is submartingale, so it increases. So you can find by how much it increases in every step, which depends on the boundary. But this is not useful to deduce how long it takes for the evolving set to become big. And instead, Ben and Yuval, they consider, so for any subset, they look at the hash process, which is either the set if the measure is smaller than half or the complement in the other case. And then they look at the square root of pi of st hash divided by pi of st. And then they control the rate of that. So then for that, it's the drift of that is going to be exactly the isoperimetric profile.
How do you get n squared? Because I would imagine
Where did I get n squared?
for the time that it takes to eat up all of the state space.
You mean for the mixing time?
Yes. Because Gabor's result tells you something that depends on V, but somehow...
But the volume
But-
you want to achieve is also depending on into the D.
So let me continue and maybe you will see. So if I knew that ST tilde intersected with GT was up to constants the size of ST tilde, then we could apply that and we would get, so I will explain what I mean, where I would get. But actually now it's a good time to show a simulation because what you will see is that we cannot hope for this result to hold for all times t. So this simulation, this simulation was generated by Jason Miller, and I think it's here, right? But you cannot see anything. Is it good? Okay, so here we started with everything closed. So this is supercritical, slightly supercritical, 0.51. So at every time, the green component is the giant, but it's tiny because we start with everything closed, and the red component is the component of the walk. If he intersects the giant, then they all become green. Now, the black points, so it hasn't become supercritical yet, but the black points are the dupe transform of the evolving set. So you see, the evolving set becomes part of the giant, but there are a lot of times when the evolving set, when I say evolving, I always mean the dupe transform, does not intersect the giant at all. So here it's most of the giant. Okay, so I think I'll stop it now. So as I said, we cannot hope for this equality to hold for all times t, but instead we can show that there exist enough times at which this equality holds. So when I say enough times, I just mean there exists at least n squared times t at which times st tilde with high probability. Actually, here it's even up to logarithmic factors, but let's not worry about that right now. So when I say there exists n squared times t, up to my target time, which is times t less than n squared plus 1 over mu times the polylog. So how do we prove that there exists enough times at which this equality holds? So here we're going to use the random walk to get information about the evolving set. While usually one uses the evolving set to get information about the walk, now we'll use the walk to obtain that. So let me write a conjecture. So if we knew that at a large constant, take a large constant c, if we knew that the probability that the walk at this time constant over mu is in the giant with positive probability, then since the walk at every time is uniform on the dupe transform, this would be the expectation of the dupe transform at this time intersected with the giant divided by the dupe transform, the size of the dupe transform. This constant over mu. So if we had that, then we would be able to get this result, but actually we would get something much stronger that for fixed times t, we would have the equivalence. So this is something that seems very reasonable, but we weren't able to prove it. So instead, what we were able to show is that there exist enough times at which the walk is in the giant. And then again, using the diaconus field coupling, we can get this result. Okay, so now, once we have enough good times, so these are good times at which times the evolving set grows because we have good control on the isoperimetric profile. So once we have that, if we now take t to be the first time that the dupe transform intersects the giant in, say, 90% of the giant, then we can show that tau is upper bounded by n squared plus 1 over mu times the polylog with high probability. Just using this sequence of good times where we have a good control on the drift. And now the main claim is that this time tau is an almost stationary time. So let's take here theta of p to be strictly bigger than 5 over 9 plus delta. Just I'm matching the numbers with a 0.9. So why is that the case? Why is tau an almost stationary time? So at time tau, we know that x tau is uniform on the evolving set by the diaconus field coupling. And the evolving set has size at least 0.9 times the size of the giant at this time, which is 0.9 times theta of p times n to the d. And this is strictly bigger than a half. So at time tau, the walk is uniform in a set with measures strictly bigger than a half, so it is close to stationarity. So this is how we prove the first result when theta of p is bigger than a half. Now, when theta of p is strictly positive, the problem is that we can consider again this stopping time tau here. And at this time, the evolving set is going to be to have size theta of p n to the d. But if theta of p is small, then at this time the walk is no longer uniform. So what we do is we restart the process. So once we obtain the first stopping time tau1, now we allow some time for everything to refresh, and we start the process again, and we obtain an independent percolation cluster and an independent time tau2. And if we have a giant cluster and we take an independent giant cluster, then the new cluster is going to cover parts that were not covered by the first cluster. So in this way, we can patch up all of these giants to get to the full space. So then, by choosing one of these times uniformly at random, the walk is uniform on a large set. And so that's how we obtain the stopping time in the second case. And I'll stop here.